So I've got this Panasonic A4 motor here. It's got incremental counts per rev and Halls all transmitted over the serial port. So there's only like 2 wires for data, plus 5 in ground and a shield. I've got another older Panasonic motor, but it has a lot more wires on it. So I think that's like a incremental with Halls embedded in it. So I haven't researched that one yet, but I'm going to talk about this A4 Panasonic motor with a plus drive because we can talk to serial encoders that are kind of like the A format. And let's take a look at the label on the motor here. So we've got, it says it's a 60 volt motor at 1 amp. That's probably amps RMS, 100 watt or 0.1 kilowatt. It says 3,000 RPM, and it's got a rated torque of 0.32 Newton meters. That's probably Newton meters per amp RMS, because if I take a look at my own speed torque curve, I'll convert 0.32 Newton meters per amp RMS to 0.226 Newton meters per amp, and the volts per radians per second. In English, that's 23, almost 24 volts per krpm. And you can see it can barely do the 3,000 with an 80 volt power supply. Because I measured the resistance, it's more like 9 ohms, 8.5 across a pair of wires. I mean, it's just Ohm's law, volts and amps, right? So anyways, we can find some data for this motor here. We'll need to enter the data. I found the motor model number MQMA012P1T is a MINAS A4 Panasonic motor. It's obsolete, and here's some old data. And I found on this the inertia 1.2 kilogram meters squared E minus 4, 1.2 E minus 4. So let's take a look at the wiring real quick. This is, again, 10,000 counts per rev or 2,500 incremental. And there's Halls. Don't forget about the Halls. But you can see the data is transmitted over the data lines with respect to ground. And there's a plus differential transmit and a shield. Never connect the shield to the case of the motor, but connect it at the drive. I'd say this is a bad drawing if that's what they do, but they don't mean connect. They do not connect it to the case of the motor. You got your light blue and purple, white and black for plus 5 and ground. There's some pins on another connector here. And it looks like there's a version that's also 17 bits absolute incremental COM encoder. So that's yet again a slightly different motor, but that's got a battery. We can ignore the battery if we're just interested in counts per rev. But Halls are for commutation, and absolute is for commutation and multi-turn on power up. I haven't seen this motor yet. That's not this one. So let's take a look at CME and see how to configure the basic setup. Brushless rotary. This motor has a brake. I bypassed it. Panasonic Incremental Format A. I selected it from the list, and it came with Halls. And don't uncheck that box. Don't change that. It's 17 bits. Okay, and 10,000 counts per rev. We can ignore the battery, but there's no battery on this one because it's purely incremental, so we don't need to ignore it. Never ignore your encoder. You can stop, come to a controlled stop before you let go, and you can put it in whatever mode of operation is good for your master. And sinusoidal commutation, of course, and you can use the multi-mode port as a emulated output. That's not a lot of counts per rev, so even though it's serial, it can still emulate. And we enter the data. Panasonic motor model. It's an 8-pole motor. 0.12 E minus 3 kilogram meters squared equals 0.12 kilogram centimeters squared. Newton meters of continuous torque, 0.32. Newton meters per amp, RMS, 0.32. Okay, so 3 times that for the peak. And the volts per radians per second is given in Same as 1 Newton meter per amp peak is 1 volt per radian per second. So you can see 23.67 volts per krpm, 9 ohms. I'm going to say 9 millihenry because I don't have my inductometer. I hit calculate and I get initial current loop, tuning parameters, current limits are set. On the V loop, you want to make sure that you go at least 10% faster or higher voltage than you want to go. So if you want to go 3,000, which you can't really do at the full rated torque, however, you could do it if the torque is less. Anyways, it's telling you, like, warning, 24 volts won't really get you to that speed. So just say, okay, plus there's some IR drop. Low gain shift. This is based on the inertia we put in, so that should be fine. But we'll tune the loops, and let's take a quick peek at the current loop tuning. Auto setup checkbox, hit start. And it's not bad. I'm just going to put in some nice round numbers here. If we put in, I'm doubling the gain. If it's too big, it gets a little buzzy for the quantization, so I'm going to knock it down. Again, this motor is a 1 amp motor, and this is a 30 amp drive, so a different drive might tune up a little better. Too much integration is always, bad. There's an overshoot, so let's bring it back down close to the calculated values, but we verified it. So apply to the velocity, auto setup checkbox, channel 3, current, actual current. Want to use less than an amp. I'm going to change the XL and decel limits here for testing purposes and hit start. When the gain is too high, the system will start to buzz, so nice round numbers, 8,000. You'll see it first in the current loop, and I'm doubling. Yeah, gain's too high. Okay, so cut it in half. I'm going to move the V loop filter from 2-pole to 1-pole, 200 hertz. There's no load, so I'm going to try to get a little bit more bandwidth out of this, and this time it did not buzz. I'm going to leave some gain margin here, and it's a little bit ringy. I see the little overshoot there. I'll just turn it down a little bit. And then the integral, I don't know. We'll do that when we do too much and you get some integrator wind up. It's kind of subjective here. You can't really see it very good. But when we tune the position, yeah, there it is, integrator wind up. When we do the position loop tuning, we'll see the settling, and that's when we'll affect. And so it's 10,000 counts for 1 rev, and let's make sure that does 1 rev here. Yep, 1 rev, and stop trace, auto setup checkbox, change the distance back to 10,000 counts or 1 rev. And, oh, can't go that fast. You can see the following error starting to go to the moon. Straight to the moon. So let's turn it down. Let's monitor the current, because current produces the IR drop. That's a lot of resistance in this winding. And I got 24 volts, so there's no way I'm going to go 3,000, let alone 1,500. Okay, that's pretty good. That was 10 revs. Let's do just 1 rev here. So this is a tuned velocity loop. We're going to take a look at the settling. So yeah, it gets pretty close to 0. I'm going to double the integrator, see if I can get a little integrator overshoot during the settling. And I got plus or minus 1 count. And, well, okay, so no integrator wind up yet. So this is just fine tuning for good settling. Yeah, so that's a little too much integral, maybe. Let's use nice round numbers and not put too fine a shine on it. And holds position plus or minus a count. If you had a large inertia, knock 10 to 1, knock this down to 100. No load, you could probably get a little less following error, but it's not bad. I mean, plus or minus a few counts while you're moving, and plus or minus a little bit. This is probably just a little torque ripple in there. Again, you could turn the gains up if you want to squeeze that more, but plus or minus 2 counts, that's crazy. So that's good. You can always save a scope file and, say, Panasonic MINAS A4, good move. So just as a record of what looks good. And again, at the end of the day, don't forget to save the flash, or when you cycle the power, it's all gone, and you can save as a CCX file, and we can take a look at the data here. Homing, I don't think there's an index here. Yeah, there is. There's a simulated index. Holy cow. All right, so home to an index. Calibrated. Back off, I don't know, 1,000 counts if you want. So rotates, finds the index, backs off 1,000 counts, and it goes back to 0. And now we can home this thing, once per rev, very, very precisely. I like that. Simulated index. That's cool. And you can jog it. From the control panel. Just remember, if your COE can't open over EtherCAT, don't leave it in disabled mode. Click the enable. Or, don't leave it in software program mode. Put it back in EtherCAT mode. On power up or reset, this is the mode that will take effect. And for shits and grins, I've got a minute or a second here. I'm going to reset the drive. So I don't believe there's any absolute position information on power up, so it ought to come up at 0, right? And then from here we can home it to the index and do your normal thing after that. Okay, well, thanks for watching Panasonic MINAS A4 motor. Apparently people are still finding them on eBay, and thousands and thousands in the field. So here's your video. Thanks for watching.